Good afternoon, students. So today I'm going to use the whiteboard instead of Wacom or any other electronic device. I hope this will be fine. Before I start, let me know whether you can see the video and hear me. You can also hear the audio. So I'll just look at your comments, and one of you or some of you can confirm whether you can see the audio and video. Okay, so I'm getting the feedback that everything is fine. So let's start. So you have been so far studying about Newtonian mechanics. You started with probably the curvilinear coordinates. Then you have been taught about the Lagrangian and Hamiltonian, which are in fact the part of the Newtonian mechanics. But in this particular topic, coming 4 weeks, we are going to discuss about a new topic called special theory of relativity. So before that, my name is, I'm your instructor, and my name is Bosanta Boruah. And if you go to the physics web page of physics, you can also go to the faculty. Then you can search my name, and you can go to my faculty page. There you will also find a page called My Teaching. There is a page called My Teaching. There also you will find a course-related web page where I will put the necessary some additional information. If I want to put, I will put there. And probably, if you remember the first lecture by Professor Perumal, the introductory lecture, there he explained about the mechanism, how this course will go, and about the details of us. And I hope there you can also find my email ID. If not, I'll just type my email ID now, and what in the meanwhile you can tell me whether the writings on the boards are visible or not. Okay, so I have just typed my email ID. In case you have some additional query, anyway, we have a mechanism of clearing your doubt through the question and answer. So whenever you feel that some part is not clear, you please ask through the question and answer. I'll try to answer those questions during the session, or if not, later on during the discussion session. In any case, for any other matter, you can also contact me through my email, and I have just typed my email ID. So coming back to the topic, special theory of relativity, in short STR. First of all, why STR is needed? Since you have already done Newtonian mechanics, and probably during your class 2, you have solved lots of problems of mechanics using Newtonian mechanics. So why you need another theory? Actually, if you look at the historical perspective, 1687 was the year when Sir Isaac Newton This was the year when Sir Isaac Newton, he published his famous book called Principia Mathematica. So actually this is a book of 3 volumes, and in this book he explained his famous Newton's laws of motion. And since 1687 till 1905, this is more than 200 years. So for more than 200 years, the physical phenomenon which have been observed were very successfully explained by Newtonian mechanics. So nobody thought that there will be need of another theory or another mechanics. They were all verified by experiments. So whatever experimental observations, they were successfully explained by the Newtonian mechanics. So one very important success of Newtonian mechanics was the prediction of planet Neptune. So when Uranus was known, when the planet Uranus was known, let's say this was the planet Uranus, and when Uranus was observed and one was looking at the predicted value of predicted location of Uranus and the observed location of Uranus. When I say observed, means it is experimentally found location of Uranus and calculated or theoretically predicted location of Uranus. There was a slight discrepancy. So there was a slight discrepancy or slight difference. Discrepancy in location. And this was the Newtonian mechanics, which was used to predict the location of Uranus. And then when a discrepancy was found, then an effort was made that why there is a discrepancy, why Newtonian mechanics is not able to predict the location of Uranus correctly. Then it was suggested that there might be another planet nearby, and because of the effect of the other planet, which was not known till then, because of the presence of the other planet, the location of Uranus is getting changed. So in the Newtonian mechanics, in the calculation of the Newtonian mechanics, if one includes the presence of the other planet, then this discrepancy is removed. So as a result, the Neptune was predicted. Neptune was predicted, and this was in fact a grand success of Newtonian mechanics. This was considered as a grand success. So this is just an example of how overwhelming the influence of Newtonian mechanics had been for about 200 years. And this Newtonian mechanics, the formalism of Newtonian mechanics was also contributed, or it was formulated in another manner by also Lagrange and Hamilton. So the classical mechanics based on Newton's laws to start with has been also branded in a slightly different manner, although it is the same Newtonian mechanics by Lagrange and Hamilton. After the successful explanation of almost all the physical phenomena till the end of 19th century, so it is towards the end of 19th century, towards the end of 19th century, that there were some observations were made which were found to be not consistent with Newtonian mechanics. or some phenomena were observed which were not inconsistent with Newtonian mechanics. So till towards the end of 19th century, everything was fine, and towards the end of 19th century, some discrepancy, some limitation of Newtonian mechanics has come into play, has appeared, and it was the brilliance of Einstein in 1905. Of course, he was supported by his fellow scientists, some of the previous scientists. So whatever Einstein predicted is also supported by the work of his predecessor. And in 1905, Einstein was able to explain or remove this discrepancy. Remove the discrepancies. So actually, what was found that when a body is traveling at the speed of light or comparable to the speed of light, then Newtonian mechanics is not sufficient. So you need a different kind of mechanics which was proposed by Newton in 1905, later on experimentally verified also. So this is the new mechanics, is the relativistic mechanics. And this pertains to bodies which are moving with or comparable to the speed of light. So the body has to travel at a speed of light or comparable to the speed of light. Then whatever Newtonian mechanics was able to predict, whatever the Newtonian mechanics can explain, will not be sufficient, and you need a different form of mechanics that is called the relativistic mechanics. So when we talk about the relativistic mechanics or the Newton, what the Einstein started with, it is intricately related to the speed of light. So you will be knowing that speed of light is normally denoted by the letter c, and the accepted value, the approximate accepted value of the speed of light is 3 into 10 power 8 meter per second. So when I say that a body has to travel comparable to the speed of light, then I am talking about c, or maybe half of c, or 1/3 of c. So only those numbers can be considered as comparable to the speed of light. So in this particular course, we will be discussing about this particular branch of mechanics, where bodies will be, if bodies are moving with a speed comparable to the speed of light, that is 3 into 10 power 8 meter per second, then some of the observations are not sufficient to be explained by Newtonian mechanics. In that case, the new branch of mechanics, which is the relativistic mechanics. So we'll discuss about this particular branch. So now a question comes here that why the Newtonian mechanics, when you have Newtonian mechanics for about 200 years, why the need of relativistic mechanics was not felt before? And whatever discrepancy we are saying that there are some discrepancy, why this discrepancy were not observed maybe 150 years before the 19th century, why these discrepancies were not felt, why these discrepancies were not noticed? In order to understand why these discrepancies are not noticed, then you have to look at this speed of light also, which is 3 into 10 power 8. This is a very large number. So a body has to travel with a speed comparable to the speed of light. Only then, whatever discrepancy we are discussing about, those discrepancies will be noticed. Now, if you consider a classical body that we see in our day-to-day life, and then if we talk about the speed that a classical body, or when I say classical body, I'm talking about a body whose position and whose speed you can detect or you can measure without any difficulty. So for example, if probably during 1700 or 1800, when one was looking at a big body moving with a high speed, probably one could think about a train. Now, what is the speed of a train? Speed of a train will be something like, let's say, 30 kilometers per hour. And nowadays, if you think of a big body which is moving at a very high speed, what we can think of is a supersonic jet. And let's say a supersonic jet which is moving with a speed of 1200 kilometers per hour. Now, just to get a feeling of, we may consider that 1200 kilometers per hour is a very large number. It is a very large speed. But what will be its value when we compare it with the speed of light? Because whether Newtonian mechanics is insufficient or not, whether relativistic mechanics will play a dominant role or not, will be dependent on the speed of the body compared to the speed of light. Now, just convert to meter per second. What I will get? This 1200 I convert to meter, so 10 power 3 and divided by 3600. This is meter per second. So I cancel it. So this is about 1 by 3, 10 power 3 meter per second, which will be 0.33 into 10 power 3 meter per second. And this comes out to be, let's say, 3.3 into 10 power 2 meter per second. Now compare it with the speed of light, which is 3 into 10 power 8. So the difference of speed between a classical body, which is we may think to be moving with a very high speed, is 10 power 6 times smaller than the speed of light. So the difference is 10 power 6. So when the speed of a body that we can think of today, or maybe a few decades back, that speed was so small that the discrepancy or the inaccuracy in Newtonian mechanics is going to be negligible. So when your inaccuracy is so small that it is very difficult to detect, and it was obvious to predict, obvious to guess that when your detector, when your observation tools are insufficient or incapable of detecting small differences, then whatever was the discrepancy of Newtonian mechanics that was not detected. So this was the reason why it took some time before the need of a new mechanics called relativistic mechanics had to come into play. But here comes another question. Now that we are saying that when the body is moving with the speed of light, Newtonian mechanics is not sufficient. So you need a different kind of mechanics called relativistic mechanics to explain the various phenomena. One question is, will Newtonian mechanics, will relativistic mechanics require when the speed is not comparable to the speed of light? For example, if I try to calculate a physical parameter, which I was using Newtonian mechanics before, do I need to use relativistic mechanics even though I know that the body is moving with a much smaller speed? The answer is yes, you can apply relativistic mechanics even for body moving at a smaller speed or the speed that you see in our day-to-day life. But sometimes too much of accuracy becomes redundant. I will give you one example. For example, someone has asked you that what is your height or what is the height of a person. Then typical height, let's say, of a person is 170 centimeter. And normally what we'll do, we'll use a scale. It is measured using a scale. And the scale will be having a least count. Least count, let's say 1 millimeter. So your measurement will be, you can write it like 170.0 plus minus 0.1 centimeter. But you know, height is another manifestation of length, and there are very precise manner of measuring the length. And one is using interferometric phenomenon or interferometric device. Interferometric device. This uses the sensitivity of light to measure length. So one can use light and the interference phenomenon in a device called interferometric device to measure the length of something. And it has a very high sensitivity. What I mean by sensitivity is if there is a change of even some tens of nanometers. What is the nanometer? 1 nanometer is 10 power minus 9 meter. So you take 1 meter and you take 10 to the power 9 parts of 1 meter, that will become 1 nanometer. So it has an accuracy of some tens of nanometers. So if the length is varying by even few tens of nanometer, that can be detected by this particular measuring technique. Now it has got much better accuracy than a meter scale. But when, let's say, you are getting the length of a person to be 170 plus minus 0.01, 0.1 centimeter, and suppose you have used the interferometric device and that device is eventually giving the value to be, let's say, 169.9987694 plus minus 0.0000 1 2 3 4 5, something like that. So you have got a very high accuracy. But it all depends on what kind of application you are looking for. So if you are looking for the height because there is a certain application, and for that application even millimeter accuracy is not needed, then this much of accuracy is redundant. However, in order to arrive at this much of accuracy, you have to do maybe you have to spend more time, you have to spend more energy, and it will be a much complicated and tedious process. So when all these are needed to arrive at an accurate value, which is in fact redundant, in that case, you always prefer to use a simple method. For example, something like a meter scale. So for most of the applications, the Newtonian mechanics, whatever predicted by Newtonian mechanics, is sufficient as far as the outcome is concerned. So that way, for most of the phenomenon during these 200 years, whatever was suggested, whatever accuracy was given by Newtonian mechanics was sufficient. So never think that whatever you have done so far is wrong, or whatever you have learned so far using Newtonian mechanics is insufficient. That is not the case. It all depends on what is the application. Of course, when the speed of the body you are considering is comparable to the speed of light, then of course Newtonian mechanics clearly is insufficient to explain the phenomenon. Otherwise, at a comparable speed, it is only a matter of accuracy, and relativistic mechanics will give probably too much of accuracy, which probably we do not need for the particular application. So before I proceed further, let me tell you about the textbooks that I am going to follow. So the main textbook that I am going to follow is Classical Mechanics by John Taylor. So you can see this book, Classical Mechanics by John Taylor. Someone from the previous batch, he asked to see how the interior looks like. So this relativistic mechanics is in chapter 15. So just to show you, actually this is quite a voluminous book. It will be good if you have access to this, but if you are not having access to the book, my suggestion is you attend the classes regularly. So this is chapter 15 and it talks about the spatial theory of relativity. So I'll just write down the name of the book. So main textbook. And another book I may follow sometime is Introduction to Spatial Relativity. Introduction to Spatial Relativity. This is by R. Resnick. So both these copies should be available in our library, but since you are not physically present here, so it may not be possible for you to access the book. But if you want to know more details beyond the course, then these are the books that you can refer to. But even if you are not able to collect these books, any of these books, you do not have to worry. The most important thing is that you have to follow each and every lecture, and best thing is you attend the live class instead of looking at the video part, because if you attend the live class and by looking at your comment, I will know how I'm going, whether I should go fast or I should go slow. So I'll keep getting your feedback, and I will also know where to emphasize and all. So please attend the classes regularly, and that will ensure that you will be, as far as the objective of this particular course is concerned, you will not have lots of difficulty to meet the objective. So maybe I'll just have a look at the comments if there is any specific comment. PDF of the reference book, I am not sure that PDF of the reference book is available. Actually, you may search our library. So I was told that through VPN you will be able to access some of the online, some of the digital books. So if there is a digital book of classical mechanics by Taylor, then you will be able to access it through VPN. But otherwise, I think if I upload the PDF or scan copy, then it will be violating. We will be violating the copyright. But if library has a digital copy, then it is possible that you can have a copy of it, or you can have a digital copy of it. I am also aware that this part, the top part, there are some reflections, so you may not see it clearly. So that is why I will be writing it below this part only. I think there was another question. Whether a body can move at a speed greater than the speed of light. So actually we'll discuss this particular part, whether a body can move greater than the speed of light. Of course, if something can move at the speed of light, why not something cannot move greater than speed of light? This question will obviously come. And in short, nothing can travel at a speed greater than the speed of light. No physical system can move at a speed greater than the speed of light. But this was a very crucial question, very complicated question to answer. I mean, because our conventional logic will say that what is the problem to have a speed greater than the speed of light? But during this course, you will see that it will be impossible to have a physical system moving with a speed greater than the speed of light. Okay, so moving forward, we will have to be conversant with some more definitions. I can see that you have got some questions. Maybe towards the end of this class, I will take up those questions. One important terminology that you are already probably familiar with in this particular course is the terminology called frame of reference. What is a frame of reference? So you have seen this terminology, but what exactly, how will you define it? If somebody asks to write a definition, how will you define it? So I can define a frame of reference as a set of coordinates. In a conventional way, I can say there is a coordinate system. In right-handed coordinate system requires x, y, and z axis. Now, once I have a coordinate system, if there is a body at a location P, and I can say that the coordinate of this body is xp, yp, zp. So I can define the location of the body by using the coordinate system, and I can also define the velocity of the body. So velocity of the body means how the x position, y position, and z position, how the instantaneous x position, y position, and z positions are changing with respect to time. If I have an idea, if there is an expression of xp with respect to time, yp with respect to time, zp with respect to time, I can use that expression to define the velocity of the body. So this actually constitutes a frame of reference. So a set of coordinate axes which can describe the position and velocity of a body is called a frame of reference. So a frame of reference can be, you are standing on the floor and you can define an x-axis, y-axis and z-axis with respect to the space in which you are standing. That constitutes a frame of reference. Now your friend is on a train and the train is moving. So your train can also define a coordinate system, x, y, z, for example, and that will be another frame of reference. So you can have like different frames of reference, and in each frame of reference, you can define the position and velocity of a given body. Now, in addition to frame of reference, there is another frame of reference called inertial frame of reference. What is an inertial frame of reference? Actually, to define it, an inertial frame of reference, there may not be just one inertial frame of reference. But if I think of one inertial frame of reference, one frame of reference which I can tell to be an inertial frame, then I have to find a frame where the laws of physics hold good. Laws of physics are valid. And later on we'll see that under, as far as classical mechanics is concerned, certain laws of physics cannot hold in all the frames of reference. So if it holds in one frame of reference, it may not hold in another frame of reference. That is why actually the need of another mechanics, the relativistic mechanics, has come. So just to define, what is an inertial frame? An inertial frame is a frame, it's a frame of reference where laws of physics hold. Of course, if you think of before 1900, then mostly the laws were governed by Newtonian mechanics or Newton's laws of motion. So it is mainly the Newtonian mechanics. You will try to see whether the Newtonian mechanics is valid or not. But later on, some other law has come. For example, there is a famous equation called Maxwell equation. We'll discuss later, and the Maxwell equation, or the outcome of Maxwell equation, it is found that when we consider going from one frame to the other frame, unless we consider relativistic mechanics, Maxwell equation will not be true in all frames. It may be true in one frame, but then if you consider another frame, the Maxwell equation cannot be valid. So in any case, just to define it, whatever laws of physics those laws of physics must hold in a frame of reference, and that frame of reference can be called as an inertial frame. But additionally, if there is another frame of reference which is moving with a constant speed relative to an inertial frame, then the second frame will also be another inertial frame. A frame of reference moving at a constant speed with respect to an inertial frame is also an inertial frame. So anyway, we'll come to inertial frame also later. We'll have some more discussion on the inertial frame, but this is in short the definition of an inertial frame. But why I am talking about the frame of reference? Because when I make a measurement, of a physical quantity, then that measurement has to be made with reference to a certain frame of reference. So there comes the concept of relativity of measurement. So any physical measurement has to be performed with respect to a reference frame or with respect to a frame of reference. The meaning is that when you are making a physical measurement of a quantity, the quantity can be the speed or the quantity can be the energy. So if you are making the measurement of a physical quantity, then you have to be concerned about the frame of reference. I mean, why we have to be concerned about the frame of reference? I can take one example. Let's say I am measuring the speed of a body and I am defining the speed of a body in this particular situation. So let's say there is a railway track and there is a train which is moving with a certain speed, let's say capital V. You are standing on the ground and your friend is on the train and your friend is playing with a toy car and the toy car is moving with a speed small v. Now let's say when the toy car is moving with a speed small v, you are making the measurement of the toy car from your frame of reference, which is the ground, and you will find a certain speed, and your friend who is steady, remaining steady on the train is moving. So with reference to the train, he is at rest, but with respect to you, he is moving with a velocity v. Now your friend will be definitely finding that the speed of the car is small v, whereas you will be definitely finding the speed to be different. So here, if somebody makes a measurement or your friend makes a measurement, then your friend has to tell that the speed of the toy car is small v with reference to the frame of reference attached to the train. And you will have to tell that the speed of the toy car is so and so with reference to a frame of reference which is attached to the ground. So if you consider speed, its value will be different. So if you are making the measurement, let's say on ground, and if you are making the measurement on the train. Now similar example can be, let's say, the kinetic energy. Let's say I'm considering the kinetic energy of the train itself. If you are making the measurement of kinetic energy, then for you the train is moving with a constant speed. So you can take the formula of kinetic energy and you can calculate what is the kinetic energy of the train. However, your friend who is at rest on the train and assuming that there is no window so that he cannot see outside, then he will not be able to give you the same value. So the measurement of kinetic energy for him, the train is at rest because he has no reference to see. So if he makes a measurement, the kinetic energy will be 0. So this is just a simple example to tell that when you make a measurement of a physical quantity, you have to be aware of the frame of reference. So you get a certain value only with respect to a given frame of reference. So that is this particular fact is this particular property is the relativity of measurement. Now, the theory of relativity is this study of the consequences of relativity of measurement So now you know that if you make a measurement of a physical quantity, it has to be with respect to a certain frame of reference. Now you can make the measurement with respect to a inertial frame of reference or with respect to another inertial frame of reference, which may be moving with respect to the previous one. So you can have different cases. Now, what are the consequences of such relativity of measurements? Now, these consequences are studied in the theory of relativity. So now you can see that when we talk about the theory of relativity, you have frames of reference which may be moving with respect to one another. So this theory of relativity is divided into two categories. In one category, the frames of references are not accelerating. So when we consider that we may have a number of frames of reference, but these frames of references are not accelerating, unaccelerated frames of reference. Unaccelerated frames of reference. So when you are talking about different frames moving with constant speed, not accelerating means one has to be moving with respect to the other at a constant speed. So when it is a constant speed we are talking about, then this branch of relativity is called special theory of relativity. So which we are going to discuss in this particular course. However, a simple question will come. What will happen when the frame of reference is accelerating? An example of an accelerating frame can be, again, you are standing in the platform of a railway station and you are seeing of your friend who is sitting in a train and the train is just starting to move. So when the train is just starting to move, the speed of the train will be gradually increasing. So it is now accelerating. So when you are considering such cases and then your friend is making a measurement at that point when the train is accelerating, so that is now he is stationary in an accelerated frame of reference. Whatever we are going to discuss in special theory of relativity, we are not going to discuss about accelerating frames. But if we include accelerating frames, accelerating frames, Then the branch is called General Theory of Relativity, in short GTR. So actually in general theory of relativity, it deals with deviation from Newtonian gravity. But this kind of deviation will be only observed when the gravity is intense gravity. Intense means very large gravity. So when the gravity is very large, Newtonian gravity cannot explain the physical phenomenon, and you need a new theory, that is the general theory of relativity. In general, it deals with also accelerated frames of reference. And this can happen, suppose in a black hole only, you can see this kind of activity where you need the general theory of relativity. But in any case, we are not going to consider accelerated frame in this course. We will be limiting ourselves only to unaccelerated frame of reference, or frame of reference which is moving with a constant speed, which is our special theory of relativity. So I think I am not going to proceed any further today. I have some 5 to 6 minutes time. Now I will probably try to answer some of the questions that may be there. Okay, another point many of you are asking is whether I will provide notes. Actually, personally, I do not like to provide notes. The reason is, you can see that when I am taking the class on the whiteboard, I am writing the important statements, I am writing the important expressions, I am giving the figure, and also I am speaking. So while I am speaking, I am giving emphasis to certain part which I feel important. Now, whatever I have taught, if I just write it in 2 or 3 pages, the message that I am able to convey through my audio and visual using the board will not be possible with the note. So by simply typing, then it will become inadequate, and you may think that just reading the note will be sufficient, and you may try to skip the class. So and then your whatever the concept you are trying to develop will become limited, will be limited to maybe 1 or 2 pages for a given class. So that is the reason why, in principle, I would like to avoid giving notes. But I will write down all the important expressions, I will write down on the board. Whatever is needed to be emphasized, I will maybe sometime I will repeat also. And all this video, for every class, the video will be available in our YouTube channel. So you already know the YouTube channel, and probably 1 or 2 days after the class, the video will be available. Professor Perumal is coordinating to upload the video. So that is as far as giving notes or slide is concerned. But again, I am saying that attend the live class. If possible, interact through the question and answer, so that I know how I am doing and what are your issues. I'll try to rectify those issues in the next class. In the previous class, one question was asked, like, why I am bringing the example of the discovery of Neptune. Is it related to special theory of relativity? So discovery of Neptune is not directly related to the special theory of relativity. I brought in to demonstrate the profound influence of Newtonian mechanics. Now, just because we have relativistic mechanics doesn't mean that Newtonian mechanics could not do anything. And the influence of Newtonian mechanics is exemplified with the discovery of Neptune. So just a few months after it was predicted that there might be another planet beyond Uranus, Neptune was observed. So that was a high time for Newtonian mechanics. Even nowadays also, you will see that we have machines, and most of the machines that we use in our day-to-day life, or that have changed our life compared to like 100 years back, those are mostly using Newtonian mechanics. So just refer to my example that when the speed of light is comparable or not comparable, when the speed of the body is not comparable to the speed of light, then we many times we do not need too much of accuracy. So the accuracy as provided by Newtonian mechanics in most of the cases is more than enough. So I'll have a look at the questions now. Yes, there is a question. It's a good question. Whether the frame of reference which is on the art will be considered inertial frame of or inertial frame or not. Actually, see, like right now I am standing here, and now you know that there are two kinds of motion. One is the rotation of art on its own axis and the revolution of art. So there is the rotation about its own axis and the revolution uh, around the sun in an elliptical orbit. So there are two motions. So precisely speaking, this is not stationary. But again, to define a stationary frame, you need something else. You always need a reference point. Without knowing the reference point, it will be difficult to define whether something is at rest or not. Now, since we are making all these observations mostly by standing on Earth, and if we have to verify something, then we will be performing the experiment on Earth only. So that is why we consider Earth to be a stationary, or Earth to be an inertial frame. But if you think deeply, truly speaking, it is again, this is also not at rest. But by definition, an inertial frame can be moving, but it cannot be accelerating. It can be moving at a constant speed. Is there any bias in nature towards inertial frame? What is Newtonian gravity? I'm talking about the gravitational law that you are already familiar with, I hope. What was the question? Okay. See, if you are probably aware of the syllabus, so the time dilation, length contraction, all these concepts will come. So I don't want to jump onto those topics, so I will definitely cover them. So please, focus on what is being covered today. I'm just trying to tell you the historical perspective of Newtonian mechanics, and why the relativistic mechanics need to come, where they will both agree and where they will not agree. So this is mostly the philosophical part. Of course, in future I will consider other cases also. Explain the example of unaccelerated frame of reference. Unaccelerated frame of reference, I am talking about a frame of reference which is moving at a constant speed. So if you consider that Earth is a stationary frame, then the example I gave, that a train is moving at a constant speed, will be an unaccelerated frame. So I'm just using the terminology. Unaccelerated is nothing but unaccelerated is nothing but acceleration is equal to 0. So this is the only point I am saying. The other thing, when I am saying the Newtonian mechanics or Newtonian laws, then I am not just talking about the three laws, Newton's first, second, and third law. Actually, there are many other derivatives starting from the Newton's law. So I am including all the laws whose origin you can trace to the Newton's law. So all these are coming under classical mechanics or prior to what is now called the relativistic mechanics. Some of you are asking that should you take note? I don't know. So probably my suggestion is maybe if you want to write a note, if you make your own note, maybe you can just look at the video later and then write it. So probably concentrating on the class, concentrating on what I try to deliver will be more important than spending time writing on the note, because then that will take some time. So since the video will be available, I think you can write down the note later on also. And yes, I would like to continue the whiteboard. I'm very happy to see that you are enjoying the whiteboard teaching. But you know, today is the first day, so just like me, probably you are also excited, but things are not always so. So I mean, sometimes there may be some shortcomings in the whiteboard also. For example, if you have to draw a nice diagram, then showing it on the electronic screen is more easier. Besides, if I have to write down the equation, if I have to solve it, sometimes in some part I may take more time. But if I do it on the PowerPoint or if I do it on the Wacom, then my flow will be smooth. But nevertheless, I will try to stick to the whiteboard, or we have another room where we have a green board. So I will see which one is the best. But what I can see from your feedback that you are liking the teaching on the whiteboard or the blackboard. So I think so the time is running out. So we'll stop here. I will download the questions and then probably we have Friday 8 to 9, but that next Friday there is no tutorial. But 8 to 9 time will be a bit less. So Saturday I will have a discussion session where these questions, and if you have more questions, you can come up and we'll have a live discussion on Saturday. Okay,
Professor Boruah, actually the Saturday they have 3 exams in the Saturday.
Okay. Okay. So anyway, that doesn't matter. If needed, if you will have to let me know. So Friday 8 to 9 we have some time. So if you want to have some more discussion, at least those who want some more discussion, we can have a 45 minutes discussion 8 to 9. So probably I will send a link. You can just fill up that link. You can fill up the form, and I will get to know your email ID. So that also I can try. Since you have exams Saturday, so I will not try Saturday. Anyway, so we'll stop here.